Hello and welcome to Late Night Cosmos, your destination for exploring the vast wonders of the universe, one intriguing question at a time. If you're as captivated by the mysteries of space as we are, don't forget to like and subscribe. It helps us keep bringing you these deep dives into the cosmos. And while you're at it, leave us a comment telling us where you're watching or listening from. Whether you're tuning in from a bustling city or a quiet corner of the world, it's fascinating to think that no matter where we are, we're all looking out at the same stars, asking the same questions. Tonight, we embark on a journey into the unknown, into the very edges of our understanding, as we explore a question that has puzzled scientists, philosophers, and dreamers for centuries. What lies beyond the observable universe? We all know the observable universe, the region of space from which light has had time to reach us since the universe began expanding. But what happens past that? Is the universe infinite, stretching out forever, or is it contained in ways we can't yet comprehend? And what does that mean for the limits of human knowledge and the boundaries of reality itself? As we journey through the depths of space and mind, we'll explore the theories, the speculations, and the groundbreaking ideas that might help us catch a glimpse of what's out there, beyond the horizon. So sit back, relax, and let your imagination wander as we peer into the cosmos and search for answers to one of the most profound questions of our time. Let's begin. From the earliest days of human curiosity, we've looked up at the night sky and wondered about the vastness of the universe. Over time, our understanding of the cosmos has evolved, shaped by the tools we've developed and the ways we perceive the world around us. Yet, even with all our advancements, we remain bound by limitations. Limitations that not only shape our view of the universe, but also influence the very questions we ask about it. For centuries, our understanding of the universe was confined to what we could see with the naked eye. The stars, the planets, and the moon were the extent of our celestial knowledge, and the universe was seen as a static, unchanging place. But as our tools and technologies advanced, so did our understanding. The invention of the telescope in the early 1700s opened a new window to the heavens, revealing galaxies and nebulae previously invisible. As our observational instruments grew more powerful, so too did our ability to peer further and further into the cosmos. However, even with the most advanced telescopes of today, there are still limits to what we can observe. Light travels at a finite speed, and the universe has been expanding ever since the Big Bang, meaning that some regions of space are simply too far away for their light to have reached us. This brings us to a fascinating idea known as the observable universe. The observable universe is essentially the region of space that we can see or detect. Limited by the distance light has travelled since the beginning of the universe, this boundary is not a physical wall, but rather a horizon, a limit to our observational capacity. Right now, that horizon stretches about 46 billion light-years away. Beyond that, space remains a mystery. But what if the universe extends beyond this observable limit? What if there is far more out there that we can't see, and perhaps never will? This question leads us into a field of speculation and theory, where ideas about the structure of the universe stretch the boundaries of our understanding. One such theory is the anthropic cosmological principle, which suggests that the universe appears to be fine-tuned for life, as if it is structured in such a way that it allows the emergence of life, including human beings. While this principle doesn't necessarily answer the question of what lies beyond the observable universe, it shifts the focus to the idea that the universe may be conditioned, or even structured, to facilitate the emergence of life. This concept was explored by cosmologists like John D. Barrow and Frank J. Tipler, who both delved into the idea of the omega point, a future moment in the universe's evolution where life, intelligence, and consciousness reach a state of maximum complexity. The omega point theory suggests that, far beyond the observable universe, the universe itself may evolve in ways that we currently cannot comprehend, pushing the boundaries of time, space, and even existence itself. As we contemplate the limits of the observable universe, we face a fundamental tension between scientific objectivity and our subjective human experience. Our observations are always limited by the tools we have, by the scope of our instruments, and by the way we process the information we gather. The universe is far larger and more complex than we can imagine, yet our perception is framed by the very tools that allow us to explore it. This interplay between our perception of the cosmos and our technological abilities creates a kind of cosmic blind spot. Just as early astronomers could not have imagined the vast galaxies beyond the stars visible to the naked eye, we too are constrained by the limits of our current technology and understanding. The very questions we ask about what lies beyond the observable universe may be shaped by these constraints. This brings us to a more philosophical aspect of the conversation. Can the beyond, the unreachable, the unseen, ever truly be understood through science alone? Can our current scientific frameworks ever fully capture the totality of the cosmos? Or are there aspects of the universe that exist outside of empirical observation, beyond the grasp of human comprehension? In the world of cosmology, this question is not just hypothetical, it's an ongoing challenge. As we develop more advanced technologies such as the upcoming James Webb Space Telescope, which is set to peer deeper into the universe than ever before, we also recognize that some questions may remain unanswered, perhaps forever. Metaphysical theories, which consider the nature of reality beyond the physical, offer alternative ways to approach the unknown. These theories allow us to consider the universe in broader terms, not just as a collection of observable phenomena, but as something that may exist in ways that we cannot yet perceive. The idea that there could be an entire reality beyond our observation is both humbling and exhilarating. Perhaps the universe isn't just what we can see, but also what we can imagine, a place where scientific knowledge and human curiosity intersect in ways we're just beginning to understand. The exploration of what lies beyond the observable universe invites us to rethink our place in the cosmos, pushing the boundaries of our imagination. We've come a long way since the days when the stars were simply points of light in the night sky. Yet for all the progress we've made, we're still confronted with the same question. Is there more out there? And if so, how do we even begin to understand it? In the next stages of our journey, we'll dive into the fascinating theories and bold ideas that might answer these questions, or, at the very least, help us venture further into the unknown. We'll look at the cutting-edge ideas that are redefining what we thought we knew about space, time, and the very fabric of the universe. And through it all, we'll keep our eyes on the horizon, ready to see what lies beyond. Quantum cosmology is an area of study that merges the principles of quantum mechanics with cosmological theories, offering a new way to understand the universe, especially in areas that are beyond our current observational limits. In this framework, the rules of quantum physics, which govern the behavior of the smallest particles, are applied to the entire universe, providing insights into how the universe might behave on the grandest scales, from its origin to its farthest reaches. This approach suggests that the universe we observe may be only a small part of a much larger, more complex reality, and it opens up the possibility that what exists beyond the observable universe could be deeply tied to the laws of quantum mechanics. One of the most intriguing theories within quantum cosmology is conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. This theory suggests that the universe is not a one-time event, but rather part of an infinite series of cycles, where each cycle emerges from the remnants of the last. Penrose's model envisions a universe that continually regenerates itself, with each big bang being the start of a new cycle. In this view, the universe does not have a definitive beginning or end, but instead exists in an eternal sequence of expansions and contractions. Penrose's theory challenges our understanding of time and space by suggesting that the universe, rather than being a single finite event, is an ongoing process, stretching across infinite cycles. This cyclical model proposes that the observable universe, which we perceive as expanding from the Big Bang, is just one chapter in an endless sequence. In Penrose's theory, the end of one cycle, when stars burn out and black holes dissipate, leads to a new beginning. The remnants of the previous universe, though no longer directly observable, serve as the seeds for the next one. In this sense, what lies beyond the observable universe is not only a question about the present and future, but also about the infinite past, with each universe existing as a part of an ongoing, never-ending cosmic cycle. In addition to this cyclical perspective, quantum cosmology introduces the concept of quantum fluctuations. These fluctuations refer to the temporary and spontaneous changes in energy that occur even in a vacuum, according to the principles of quantum mechanics. Essentially, quantum fluctuations suggest that even in seemingly empty space, there is always some activity, as particles can appear and disappear momentarily. When applied to the universe as a whole, This concept implies that the observable universe itself might not be a stable, fixed entity. Instead, it could be a localized fluctuation in a much larger quantum field, a field that spans beyond our ability to observe. The idea is that our universe, with its galaxies, stars, and galaxies, might be just one of many such fluctuations in a vast quantum sea. These quantum fluctuations introduce a fascinating possibility. The observable universe, with all its structure, might simply be one instance of an infinite number of potential universes, each with its own distinct properties. This concept leads to a vision of the cosmos far larger and more varied than we could have ever imagined. The universe that we see, the one that appears orderly, structured, and predictable, may be just a brief and transient feature of a far more complex and unpredictable quantum reality. Hugh Everett's many worlds interpretation of quantum mechanics takes this idea even further by proposing that every quantum event doesn't result in a single outcome, but rather branches into multiple realities, each representing a different possibility. According to Everett, every time a quantum event occurs, such as a particle being in one state or another, reality splits into multiple parallel worlds, with each world corresponding to a different outcome. These alternate realities exist alongside our own, but they are completely inaccessible to us, creating a vast multiverse of parallel universes, each with its own set of physical laws and conditions. In this context, the universe we observe may be just one of an infinite number of parallel worlds, each with its own set of rules and outcomes. The many worlds interpretation suggests that our universe is just one path in an infinitely branching tree of realities. This radical idea challenges our traditional view of reality, where there is one definite past and future. In Everett's model, the universe is much more fluid, with countless parallel versions of reality coexisting, all branching from the same quantum events. Quantum mechanics itself, in all its strangeness, raises profound questions about space, time, and the very nature of observation. One of the key features of quantum mechanics is the idea that particles exist in a state of probability until they are observed. This means that, at a fundamental level, reality is not determined until it is measured or observed. This concept, often referred to as the observer effect, challenges our traditional understanding of space and time, suggesting that the act of observing can actually shape reality itself. If the very fabric of the universe is influenced by observation, then what does this mean for the limits of the observable universe? Is it possible that what we consider the edge of the universe is not a hard boundary, but a fluid, shifting horizon, shaped by the very act of our observation? The idea that quantum mechanics can influence the large-scale structure of the universe opens up intriguing possibilities for what lies beyond the observable universe. Could the very rules that govern quantum particles also apply to the entire cosmos? If so, then the universe might not be a static, unchanging entity, but a dynamic and ever-changing system, constantly shaped by quantum processes beyond our perception. Moreover, if the universe is indeed a product of quantum fluctuations, then it might be part of an ongoing quantum dance, forever in motion, forever expanding, forever changing. What we see, the stars, the galaxies, the expanding universe, is only a snapshot, a brief moment in the ongoing ebb and flow of quantum activity. The observable universe, then, is not a complete picture of reality, but rather a fleeting glimpse into a vast and incomprehensible quantum sea. These ideas, though speculative, push the boundaries of our understanding, encouraging us to think differently about the universe and what lies beyond our reach. Whether it is through Penrose's cyclical universe, Everett's many worlds, or the idea of quantum fluctuations shaping reality, quantum cosmology invites us to imagine a universe that is far more complex, interconnected, and dynamic than we ever could have imagined. It challenges us to rethink the very nature of space, time, and observation, and to consider the possibility that what lies beyond the observable universe may be even more extraordinary than we can comprehend. The Big Bang theory has long been the cornerstone of our understanding of the universe's origin. According to this theory, the universe began as a singularity, a point of infinite density and temperature, roughly 13.8 billion years ago. From this incredibly small, hot, and dense state, the universe began to expand, and over billions of years, matter and energy spread out to form the stars, galaxies, and all the structures we observe today. But the Big Bang theory raises an important question. What does it mean for the universe to have a beginning? Does this mark the start of time itself? Or is it simply a moment in an ongoing infinite process? The concept of time, as we experience it, is deeply tied to the idea of a universe that has a beginning, a point when time itself started to flow. In traditional cosmology, time is seen as something linear, starting at the Big Bang and progressing forward from that moment. However, this view is being challenged by a number of alternative theories that propose a very different understanding of time. One such theory is eternal inflation, a concept introduced by physicist Alan Guth in the early 1980s. Eternal inflation builds on the idea of cosmic inflation, which posits that the universe underwent a rapid expansion in the first moments after the Big Bang. However, eternal inflation goes further by suggesting that this inflationary process never completely ended, and instead, new regions of space continue to undergo inflation, creating new pocket universes. According to this view, the universe we observe is just one of many such universes, each with its own set of physical properties. In the eternal inflation model, there is no definitive beginning, no single point at which time and space began. Instead, the process of inflation continues eternally, with new universes emerging in a never-ending cycle. In this sense, the universe we know might simply be one moment in an infinite sequence of ever-expanding realities. This idea introduces the possibility that the universe does not have a single, finite beginning. Rather, time itself might stretch infinitely backward, with no true start point. It challenges the idea of the Big Bang as the beginning of time and suggests that the universe is part of a larger eternal process. If eternal inflation is correct, then the observable universe, everything we can see and measure, is just a small piece of an ever-growing infinite cosmos. Another fascinating perspective comes from Lee Smolin, who proposed the theory of the fecund multiverse. Smolin's idea suggests that new universes emerge from black holes, each one potentially having different physical properties from the one that gave birth to it. In Smolin's view, black holes do not mark the end of a universe, but rather, they are the seeds of new universes. Each time a black hole forms, it creates a new universe within it, continuing the cycle of creation and evolution. These new universes would inherit some characteristics from the original universe, but also evolve in unique ways, governed by their own set of laws and constants. In this model, the universe is not a one-time event, but a never-ending process, where new universes are born from the remnants of older ones. Each universe that emerges from a black hole could contribute to a larger multiverse, with the properties of each new universe being shaped by the conditions that existed within the black hole. This view suggests that the universe could have no true beginning and no true end, but instead exists in a perpetual cycle of creation and rebirth. If Smolin's idea is correct, then time, as we understand it, might simply be one part of an eternal, cyclical process. While Smolin's model focuses on the creation of new universes, Carlo Rovelli and Julian Barber take a more radical approach by questioning the very nature of time itself. Both physicists have suggested that time might not be fundamental to the structure of the universe. In Rovelli's loop quantum gravity theory, time is not a continuous, unchanging backdrop against which events unfold. Instead, time emerges from the interactions of quantum fields and is only an approximation of a deeper, more fundamental reality. According to Rovelli, time, as we experience it, is an illusion, a byproduct of the way the universe is structured at macroscopic scales. In this view, the universe may not have a definitive beginning or end, but rather, time itself could be a transient concept, appearing only when certain conditions are met. Similarly, Julian Barber proposes that time, in its conventional sense, is not a fundamental feature of the universe. Barber's theory, known as timeless physics, suggests that the universe is actually a collection of nows, a series of distinct moments that exist independently of one another. In this view, there is no continuous flow of time. Instead, time is simply a human construct, an artifact of our perception. Barber's ideas challenge the traditional understanding of the universe as a timeline that stretches from the past, through the present, and into the future. If time is not fundamental, then the universe itself might not have a clear origin. Instead, it could be a timeless entity, existing in a series of discrete eternal moments, without a single starting point or an end. These theories are profound because they suggest that our conventional understanding of time, beginning, middle, and end, might not apply to the universe at large. If time is not a fundamental property, then the idea of the Big Bang as the start of everything becomes less meaningful. The universe may not have begun in the way we think, and what we observe as the flow of time could merely be a reflection of deeper, more complex processes that we are only beginning to understand. One more concept to consider is the rotating universe theory, proposed by the mathematician Kurt Gödel in the 1930s. Gödel's theory introduces the idea of a universe in which time itself loops back on itself. In Gödel's rotating universe, the fabric of space-time is curved in such a way that an object could travel along a path and eventually return to its starting point, creating a closed loop. This implies that time is not linear but could be cyclical, allowing for the possibility of time loops, where the future and the past fold into each other. Gödel's model challenges our conventional understanding of time and suggests that the universe could be far more complex than we realize, with time itself perhaps looping in ways that we cannot yet observe or understand. If time is cyclical, as suggested by Gödel, then the universe we see may be part of a larger rotating cosmic system, where events are not set in a linear progression but instead exist in an eternal loop. This would have profound implications for how we view the beginning of the universe. If time is a loop, then the concept of a beginning may be irrelevant, as the universe could exist in a never-ending cycle, constantly repeating itself. Taken together, these theories, eternal inflation, the fecund multiverse, timeless physics, and Gödel's rotating universe, suggest a radically different view of the cosmos. Instead of the universe having a single finite beginning, time could be cyclical, infinite, and possibly even illusory. These ideas challenge our fundamental assumptions about the nature of time, space, and the universe itself, and they open the door to new, speculative possibilities about what might lie beyond our current understanding. What if the universe, in all its complexity, has no true beginning or end? What if time itself is just one chapter in an eternal, ever-evolving cosmic story? These questions continue to shape our quest to understand the universe and its infinite possibilities. When we think about the universe, we often imagine it as vast and boundless, stretching out infinitely in all directions. But what if the very idea of a horizon, that boundary that marks the limits of what we can see, isn't a real physical boundary at all, but instead a kind of illusion? What if space itself is infinitely continuous, extending far beyond what we can observe, and what we think of as the edge is simply the limit of our perception? These are the kinds of questions that challenge our understanding of the universe and prompt us to rethink the nature of space, time, and observation. The observable universe, the region of space from which light has had time to reach us, seems to present a clear boundary. This horizon is about 46 billion light-years away from Earth, beyond which we cannot observe because the light from that region hasn't had time to reach us since the beginning of the universe. This observable limit has been a central concept in cosmology, shaping our understanding of the universe's size and structure. However, what if this boundary is not an actual edge to the universe, but just a limit to our ability to see it? One of the most thought-provoking ideas about this comes from David Bohm, a theoretical physicist who proposed the concept of the implicate order. Bohm's theory suggests that the observable universe is merely a projection of a deeper, hidden reality. According to Bohm, what we see as the surface of the universe, its stars, galaxies, and all the cosmic structures we observe, is just a small fraction of a much more intricate and interconnected whole. He argued that there is a deeper order to the universe, one that is not immediately apparent to our senses but exists beneath the surface of our observable world. In this view, the universe is not just what we can see, but something far more complex, a reality that is hidden from us, perhaps even beyond our current capacity to comprehend. Bohm's ideas suggest that the boundaries of the observable universe may not be true limits of space, but rather limitations of our perception. If this deeper, hidden reality exists, then what we consider to be the edge of the universe might simply be a kind of illusion, a reflection of our current understanding. This idea raises fundamental questions about what we can and cannot know about the universe. Are we, as observers, bound by our limited tools and senses, or is there a deeper reality that we simply can't access at this stage of our understanding? Many astronomers, such as Martin Rees, have pondered these limits in their work. Rees in particular has pointed out that there are aspects of the universe that may always remain unknowable to us, even with the most advanced technology and the most precise instruments. The limits of human knowledge may be far greater than the physical limits of our observation. In other words, there may be phenomena in the universe that are fundamentally beyond our grasp, not because we lack the technology to detect them, but because the nature of these phenomena is such that they cannot be observed or measured using the methods we have at our disposal. This concept challenges our traditional view that, with enough time and effort, science will eventually uncover all the secrets of the universe. The tension between what is observable and what is unknowable has also been explored by philosophers throughout history. Figures like Immanuel Kant and Heinrich Hertz have grappled with the question of whether the universe can truly be known beyond the limits of human perception. Kant, in particular, argued that our knowledge of the world is limited by the way our minds process information. According to Kant, we can never know things as they truly are, because our perception of reality is always filtered through the lens of our senses and cognitive structures. For Kant, the universe as it exists in itself is something that we can never fully comprehend. We are limited by the very tools, our senses and our minds, that we use to explore it. Similarly, Hertz, in the late 19th century, suggested that human perception is inherently limited, and that our understanding of the universe is shaped by the frameworks we create to make sense of it. He proposed that the way we observe the universe is influenced by our concepts of space, time, and causality, and that these concepts might not necessarily reflect the true nature of the universe. For Hertz, the boundaries of knowledge are not just a matter of technological advancement, but are also bound by the very way we conceptualize the universe. This philosophical view intersects with the ideas of scientists like David Bohm and Martin Rees, who suggest that there may be parts of the universe that are beyond human perception or understanding. If there are limits to our knowledge that go beyond the physical limits of observation, then what does this mean for our quest to understand the universe? Can we ever truly grasp what lies beyond the observable universe if our perception is inherently flawed or limited? And if so, how do we overcome these limitations? This tension between the observable and the unknowable opens up a fascinating area of exploration, one that bridges science with philosophy. As we reach the boundaries of the observable universe, we are confronted not only with the limits of our technology, but also with the deeper, more fundamental question: can the universe extend beyond our understanding? Is there a point where science and metaphysical speculation must meet, where the very concept of beyond takes on new meaning? One of the most intriguing aspects of this question is the possibility that the universe could indeed be infinite, extending far beyond the limits of what we can observe. If space is infinitely continuous, as some cosmologists suggest, then the observable universe is just a small fraction of a much larger reality. In this scenario, what lies beyond the observable universe isn't just a distant region of space, but the unobservable vastness of an infinite cosmos. This idea invites us to imagine a universe that goes on forever, where there is no true edge, no final boundary, and no limit to what can exist. However, this idea of infinite space is not just a matter of scientific speculation, it also has profound philosophical implications. If the universe is infinite, then the very concept of a horizon becomes less meaningful. Without a true boundary, what does it mean to observe or to know? Can we ever fully understand the universe if it extends beyond the limits of our perception? And if the universe is infinite, what is the role of human knowledge in a cosmos that stretches beyond our comprehension? These questions continue to shape our understanding of the universe and our place within it. As we probe deeper into the cosmos, both through observation and through speculation, we're constantly confronted with the tension between what we can see and what remains hidden. The boundaries of the observable universe, whether real or illusory, are not just physical limits but also symbolic ones, representing the limits of our knowledge, our technology, and our imagination. In the end, the quest to understand what lies beyond the observable universe is not just about discovering new regions of space, but about grappling with the deeper questions of existence itself. It challenges us to think beyond the observable, to question the very nature of reality, and to consider whether there are boundaries to knowledge that are beyond even our most ambitious scientific efforts. The universe, it seems, is not just a place to explore, but a puzzle that may never fully be solved, one that invites us to keep searching, to keep questioning, and to keep imagining. The idea of the multiverse, the notion that our universe may be just one of many, is a concept that stretches the imagination in fascinating ways. It challenges the very foundation of what we consider to be the universe, expanding our understanding of reality itself. If the multiverse theory is correct, then what we see and experience in our universe might be just a small piece of a much larger cosmic structure, one that is filled with countless other universes, each with its own unique properties. One of the most well-known models of the multiverse comes from the theory of eternal inflation, proposed by the physicist Andre Linde in the 1980s. Eternal inflation builds on the idea of cosmic inflation, which suggests that the universe expanded at an incredibly rapid rate in the first moments after the Big Bang. However, eternal inflation takes this concept even further. According to Linde's theory, inflation never truly ends. Instead, it continues on forever, with new regions of space-time constantly undergoing inflation and creating new universes, or pocket universes. These pocket universes would each have their own distinct physical laws and constants, creating a vast and ever-growing multiverse. In this scenario, our observable universe is just one bubble in an infinitely expanding sea of universes. The idea of eternal inflation suggests that there could be an infinite number of universes, each with its own characteristics stretching far beyond the limits of our observation. In this view, the observable universe, the part of the cosmos that we can detect, is just a tiny fraction of an unimaginably larger whole. The idea of a multiverse challenges our traditional understanding of the universe, as it proposes that our universe may not be the only one, nor the most important. Rather, it is just one piece of a much grander cosmic puzzle. Max Tegmark, a physicist known for his work on cosmology, further expanded the multiverse idea by categorizing it into 4 distinct levels. The first level, which is the most straightforward, suggests that the universe we observe may simply be one of many universes that are similar to ours, but each with slightly different initial conditions. These universes would share the same fundamental laws of physics, but would differ in things like the arrangement of matter and the development of galaxies. The second level of Tegmark's multiverse involves universes that have different physical constants. In this model, universes could exist with completely different values for fundamental constants, like the strength of gravity or the charge of an electron. These universes would have different laws of physics, which would lead to entirely different types of matter and life, making them completely unrecognizable to us. The third level of Tegmark's model suggests a multiverse in which different regions of space-time are governed by different physical laws, leading to universes that could be radically different from our own. These universes could exist alongside ours, but they would be entirely disconnected from our observable universe, with no way for us to interact with or detect them. Finally, the fourth level of Tegmark's model takes us into even more speculative territory. This level proposes that the multiverse includes all possible mathematical structures, meaning that any conceivable universe, no matter how bizarre or counterintuitive, could exist somewhere in this vast expanse. The fourth level of the multiverse suggests that the entire concept of reality could be far more flexible and diverse than we can even begin to imagine. Universes could exist with entirely different mathematical structures, different rules of logic, and even different forms of existence altogether. The bubble multiverse is one of the most fascinating aspects of the multiverse theory. In this model, the universe we observe is just one bubble, in a much larger and ever-expanding multiverse. Each bubble represents a different universe, each with its own set of physical laws and constants. These bubbles can expand and stretch beyond our current observational limits, creating a vast and incomprehensible structure of realities. The idea of the bubble multiverse suggests that, just as our universe began with the Big Bang, each of these other universes may have had their own Big Bangs, leading to their unique developments. This theory proposes that there could be an infinite number of these bubbles, each one potentially existing in a completely different state, with different laws of physics. The fact that we are limited to observing only one bubble, the one we happen to occupy, means that we are blind to the other universes that exist beyond our own. This raises profound questions about the nature of reality. How many universes are out there? Are there universes where the laws of physics are so different that life, as we know it, could not exist? And, most intriguingly, Could we ever find a way to detect or communicate with these other universes, or are they forever out of reach? The idea of higher dimensional multiverses takes the concept of the multiverse even further. Scientists like Brian Greene and Michio Kaku have explored the possibility that our universe may exist in a higher dimensional space, one that's beyond our three-dimensional understanding. According to string theory and related ideas, the universe could have additional spatial dimensions beyond the ones we can observe. These extra dimensions could be so small and tightly curled that they are imperceptible to us, but they could have a profound impact on the structure of the universe. In this higher dimensional view of the multiverse, the universe we observe may simply be a three-dimensional projection of a much larger, multi-dimensional reality. The idea of a higher dimensional multiverse suggests that there could be universes existing in these extra dimensions, with properties and laws that are completely different from our own. These higher dimensional universes would be completely inaccessible to us, as they exist in dimensions that we cannot perceive with our current senses or instruments. The implications of such a theory are vast, as they suggest that reality itself could be far more complex and multi-layered than we can imagine. As we delve deeper into the multiverse theory, we are forced to rethink our fundamental understanding of what a universe actually is. Traditionally, we've thought of the universe as a single, unified reality, one that began with the Big Bang and has been expanding ever since. The multiverse theory, however, challenges this concept, suggesting that the universe we observe is not unique, but is just one of many, each with its own set of rules and characteristics. This raises new questions about the nature of existence. If there are infinite universes, each with different physical laws, what does that mean for our own universe? Is it special, or is it simply one of countless others that are governed by different rules? The multiverse theory also challenges the notion of what is possible within the universe. If there are infinite universes, each with different physical constants and laws, then the possibilities for what could exist in the cosmos become nearly limitless. In one universe, life might exist in forms radically different from anything we can imagine. In another, the laws of physics could be so different that matter itself might behave in ways that are completely unfamiliar to us. This opens up new realms of possibility and imagination as we begin to think beyond the confines of our own universe and consider the infinite ways that reality could manifest. The multiverse, in all its variations, suggests that what we observe in our universe may be just a tiny fraction of a much grander reality. It challenges our understanding of the cosmos and invites us to rethink the very concept of universe. Is our universe the only one, or is it just one of many, each with its own unique properties and characteristics? As we continue to explore the cosmos, we may find that the answers to these questions are far more complex and wondrous than we could have ever imagined. When we venture into the realm of cosmology, there are certain ideas that seem almost too strange to be true, ideas that challenge the very foundation of what we believe to be the universe. These are the exotic theories, the unconventional ideas that push the boundaries of our understanding of space, time, and reality itself. Some of these ideas propose that the universe is far more complex and mysterious than we could have imagined, ideas that stretch our imagination and force us to reconsider what is possible in the cosmos. One of the most intriguing and radical ideas in modern physics is loop quantum gravity, which aims to merge the theory of quantum mechanics with general relativity, offering a new way to understand the fabric of space-time. At its core, loop quantum gravity suggests that space-time is not continuous, but instead it is made up of tiny, discrete units. These units, known as quantum loops, form the very structure of the universe, much like the pixels that make up a digital image. According to this theory, space and time are quantized, broken down into the smallest possible chunks that cannot be divided further. This idea suggests that at the most fundamental level, space-time itself is a kind of granular substance, and our smooth, continuous experience of the universe is an approximation of this deeper, more discrete reality. This quantum view of space-time leads to the possibility that the universe may be part of a higher dimensional reality, one that we cannot directly perceive with our senses. In the context of loop quantum gravity, the fabric of the universe could extend into additional dimensions beyond the three spatial dimensions we experience. These extra dimensions may be hidden from us, curled up so small that they are undetectable with current technology. But in theory, these dimensions could hold the key to understanding the true nature of the universe and the fundamental forces that govern it. Another exotic theory that challenges our understanding of the cosmos is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny, vibrating strings. These strings, much like the strings of a musical instrument, vibrate at different frequencies, and the different modes of vibration correspond to different types of particles. In this view, the universe is not made up of separate particles interacting with one another, but rather, everything is interconnected through these tiny, vibrating strings. One of the most exciting implications of string theory is the idea that our universe may exist in a higher dimensional space, one that extends beyond the familiar 3 dimensions of space and 1 dimension of time. In string theory, the universe could have as many as 10 dimensions, with the extra dimensions being compactified, or curled up so small that we cannot detect them. This idea of higher dimensional space suggests that there could be many more dimensions of reality that we are unaware of, and that our perception of space and time is limited to just a small slice of a much larger, multi-dimensional cosmos. This notion of higher dimensional space is further explored in M-theory, an extension of string theory, proposed by physicists like Edward Witten and John Schwartz. M-theory suggests that the fundamental building blocks of the universe are not just one-dimensional strings, but rather higher dimensional objects known as brains. These brains can have multiple dimensions, and the entire universe could be a 3-dimensional brain floating in a higher dimensional space. According to this theory, our entire universe might be a kind of slice of a higher dimensional reality, and the extra dimensions that M-theory predicts could be the key to understanding the true nature of the cosmos. Another fascinating idea that challenges our understanding of the universe comes from Lee Smolin, who proposed the concept of cosmological natural selection. This theory is based on the idea that universes evolve in a way similar to biological organisms, with each universe having the potential to create offspring universes. According to Smolin's theory, new universes are born from black holes, and each new universe inherits some of the properties of the universe that gave birth to it. However, the key difference is that universes that are better able to create black holes, universes with the right conditions for black hole formation, are more likely to reproduce and create new universes. Over time, this process of natural selection leads to the evolution of universes with properties that are conducive to the creation of black holes. In Smolin's view, the universe we observe may be just one in an infinite series of universes, each one shaped by the process of cosmological evolution. While these ideas may seem strange and far-reaching, they are part of a growing body of thought that suggests the universe is far more complex than we currently understand. One theory that takes us even further into speculative territory is Ruth Kastner's transactional interpretation of quantum mechanics. Kastner's theory proposes that the universe is not just a simple chain of cause and effect, but rather a dynamic interplay of quantum events that involve multiple timelines and quantum histories. In this view, quantum interactions are not just local events that happen at specific points in space and time, but rather they involve a kind of transaction between multiple possible timelines. Each quantum event could be part of a larger non-linear process, where different outcomes exist in parallel and interact with one another. This interpretation suggests that the universe might not be as straightforward as we imagine, and that multiple histories and possibilities are continuously playing out in parallel. Finally, we turn to Donald Hoffman's interface theory of perception, which offers yet another radical perspective on the nature of reality. Hoffman's theory suggests that our perception of the world is not an accurate representation of objective reality, but rather it is a user interface, a system designed to help us navigate the world in a way that is useful for survival, but not necessarily true to the underlying structure of the universe. According to Hoffman, the way we experience space, time, and objects is shaped by the evolutionary pressures that favored perception systems that are fit for survival, rather than systems that reveal the true nature of reality. In other words, what we see is not the way the universe truly is, but a simplified, user-friendly version of it. If Hoffman's theory is correct, then our understanding of the universe is deeply limited, and there could be much more to reality than we can ever perceive. These exotic theories and unconventional ideas loop quantum gravity, string theory, M-theory, cosmological natural selection, transactional interpretation, and the interface theory of perception represent a dramatic shift in how we think about the cosmos. They challenge the traditional view of a universe that operates according to simple, deterministic laws and instead suggest a reality that is far more complex, interconnected, and dynamic. Each of these theories points to a universe that is not just a static collection of matter and energy, but a living, evolving system that operates on principles we're only beginning to understand. As we explore these ideas, we are forced to reconsider everything we thought we knew about space, time, and the very nature of reality itself. And in doing so, we open the door to a new, deeper understanding of the universe, and perhaps even to the possibility that there are realms of existence that stretch far beyond our current comprehension. Imagine for a moment that the universe we see, with its stars, galaxies, and cosmic structures, is not all there is. What if our universe is just a small part of a much larger hidden reality? A reality where what we perceive as the physical laws of nature could be shaped by dimensions beyond the ones we experience every day. This is where brain-world cosmology enters the picture, a model that suggests our universe exists on a kind of membrane, or brain, in a higher dimensional space. The concept of brain-world cosmology builds on the idea that the universe we observe may not be the entire universe, but rather a three-dimensional surface, like a sheet, floating within a higher dimensional space. According to this theory, our familiar three-dimensional world, along with time, exists on a brain, much like a two-dimensional drawing exists on a flat sheet of paper. These brains could exist in a vast higher dimensional space, beyond our ability to directly perceive, and there could be other brains, with their own universes floating in this same higher dimensional space. The most fascinating aspect of this theory is the idea that, although we are confined to our three-dimensional brain, the higher dimensional space could contain regions of reality that are fundamentally beyond our reach. This is where the idea of extra dimensions becomes crucial. The observable universe, what we can see and measure, may simply be a small slice of a much larger reality. The higher dimensional space in which these brains exist could hold the key to understanding what lies beyond the observable universe. What we perceive as the edge of the universe, the cosmic horizon, might simply be a limitation of our perception, beyond which lie vast, unseen regions of space-time governed by different rules. One of the most influential theories related to brain-world cosmology is M-theory, which was proposed by physicists such as Edward Witten and John Schwartz in the 1990s. M-theory is an extension of string theory, a model that suggests that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings vibrate in multiple dimensions, and the different frequencies of vibration correspond to different types of particles. M-theory takes this idea further by proposing that there are multiple types of objects, not just one-dimensional strings, but also higher-dimensional objects known as brains. In M-theory, the entire universe, including the forces we observe, gravity, electromagnetism, and the strong and weak nuclear forces, could be confined to a brain, floating in a higher dimensional space. According to M-theory, our universe may be just one brain among many, and the higher dimensional space in which these brains exist could hold many other universes, each with its own set of physical laws and constants. This idea opens up the possibility that our universe is part of a vast multiverse, with countless other universes existing in the same higher dimensional space. These other universes could be radically different from ours, with different physical laws, different constants, and perhaps even different types of matter and energy. The implications of this are profound. It suggests that the observable universe we see, our galaxies, our stars, our cosmic structures, could be just a tiny fragment of a much larger multi-universe reality. The work of Lisa Randall also contributes significantly to our understanding of higher dimensional spaces and their impact on cosmology. In the early 2000s, Randall and her collaborator Raman Sundram proposed a model known as RS1, which suggests that our universe could be confined to a three-dimensional brain, while gravity, unlike the other fundamental forces, could extend into the higher dimensional space. This theory, known as warp-drive cosmology, posits that the strength of gravity could vary depending on how far away a point is from the brain. The idea challenges our traditional understanding of gravity, which has always been seen as a force that works equally throughout space. Randall's work suggests that the force of gravity could be much weaker in higher dimensional spaces, which could help explain some of the mysteries surrounding dark matter and dark energy. These concepts are still being explored, but they provide an exciting glimpse into the possibilities that higher dimensions might offer for understanding the universe. M-theory and the brain-world model also open the door to speculative ideas that are not yet fully understood but could offer profound insights into the nature of the cosmos. For example, Kaluza-Klein theory, developed in the early 20th century, suggests that additional spatial dimensions could help explain the forces of nature. Kaluza-Klein theory initially proposed that electromagnetism could be unified with gravity by introducing an additional dimension of space. This extra dimension, although hidden from view, could provide a new framework for understanding how the fundamental forces of nature work together. The theory was groundbreaking at the time and paved the way for later developments in string theory and brain-world cosmology. Today, physicists are still exploring the idea that there could be additional dimensions beyond the familiar three spatial ones, dimensions that could explain forces like gravity and electromagnetism, as well as the mysterious phenomena we observe, such as dark matter and dark energy. The idea of extra dimensions is also linked to the search for a unified theory of physics, one that can explain all the fundamental forces of nature within a single framework. The standard model of particle physics successfully explains the electromagnetic, weak, and strong nuclear forces, but it leaves out gravity, which is described by general relativity. String theory and M-theory, by introducing higher dimensions, offer the potential for unifying these forces into a single, elegant theory. However, this search for unification also raises deeper questions. What lies beyond the limits of the dimensions we can observe? Are there regions of reality that exist outside the boundaries of our current understanding? And if so, how can we ever hope to explore or even comprehend them? While these theories and ideas are speculative, they represent the cutting edge of cosmological thought, offering us a new way to think about the universe and our place within it. They challenge our preconceived notions of space, time, and reality, suggesting that the universe is far more intricate and interconnected than we can perceive. If our universe is just one brain in a higher dimensional space, then the possibilities for what lies beyond are virtually limitless. Theories like M-theory, brain-world cosmology, and Kaluza-Klein theory give us a glimpse into a reality that exists beyond the observable universe, where extra dimensions could hold the answers to some of the deepest mysteries in physics. As we continue to explore the cosmos and develop new tools to study the universe, it is possible that we may one day gain a deeper understanding of these hidden dimensions and the forces that govern them. Until then, these theories will continue to challenge our understanding of reality, inviting us to imagine a cosmos far grander and more mysterious than we ever thought possible. The search for the nature of these extra-dimensional realms is just beginning, and as we venture further into the unknown, we may find that the universe is not just larger than we think, but also far more strange and wondrous than we can imagine. For centuries, humanity has wondered about the role of consciousness in the cosmos. What if our very awareness, the act of perceiving, does more than just allow us to experience the universe? What if consciousness itself influences the universe, shaping reality in ways we don't yet fully understand? This idea challenges our conventional view of the cosmos, suggesting that our minds and the physical universe are not separate but intimately linked. Could it be that our perception, or even the act of observing, is part of a larger cosmic process affecting the fabric of space-time itself? One of the most fascinating theories that links consciousness to the universe is Ork-OR theory, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. The theory, which stands for Orchestrated Objective Reduction, proposes that consciousness arises from quantum processes that occur within the microtubules of neurons in the brain. These microtubules are structures inside cells that Penrose and Hameroff believe might act as quantum computers, processing information in ways that go beyond classical physics. According to Ork-OR theory, consciousness is not just a product of classical brain activity, but arises from quantum effects in space-time. In this view, the universe itself is fundamentally connected to the quantum processes that occur at the smallest scales of reality. Penrose suggests that the collapse of the quantum wave function, a process by which quantum systems shift from multiple possibilities to a single outcome when observed, could be influenced by consciousness itself. In other words, consciousness doesn't just arise from the brain, it may actually be connected to the very fabric of the universe. This implies that our awareness might play a direct role in shaping reality, influencing the outcome of quantum events, and possibly even altering the course of cosmic processes. If consciousness is indeed connected to quantum events, then the very act of observing could have a profound effect on the universe, even on scales beyond our immediate perception. The idea that consciousness might play a role in shaping the universe is also suggested by theorists like Fred Alan Wolf. Wolf has proposed that consciousness is not simply a passive observer of the universe, but an active participant in its creation. According to Wolf, our thoughts, perceptions, and intentions might have the ability to influence the physical world. He suggests that consciousness may be capable of interacting with the quantum field, the underlying foundation of reality, in ways that affect the outcomes of physical processes. This idea echoes the concept of mind-matter interaction, which has been explored in various forms throughout history, from the mystical to the scientific. Wolf's work ties into the broader idea that consciousness could be more than just a byproduct of the brain. Instead, it could be a fundamental feature of the universe itself. In this view, consciousness is not something that happens only in human minds, but is an inherent property of the universe, woven into the very structure of reality. This leads to the idea that the universe is not simply a collection of matter and energy, but a dynamic, interactive system where consciousness plays an integral role in the unfolding of cosmic events. The connection between consciousness and the universe is further explored in the work of David Bohm, a theoretical physicist who developed the concept of the holistic universe. Bohm's view of the universe challenges the traditional, mechanistic understanding of space and time. He suggested that the universe is not a collection of independent, separate parts, but rather an interconnected whole, where everything is fundamentally linked. Bohm's idea of wholeness suggests that the universe operates as a single unified process, and consciousness, in this framework, could be seen as a part of that larger whole. If the universe is a holistic system, then our awareness, our perception of reality, could influence the flow of that system in ways that go beyond just our immediate surroundings. Bohm's work also ties into the concept of quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one particle is instantaneously linked to the state of another, no matter the distance between them. This kind of non-local connection challenges our understanding of space and time and suggests that information can be transferred in ways that transcend the usual limitations of the physical world. Bohm believed that the universe might be governed by deeper, non-local connections, and that consciousness could be one of the factors influencing these connections. In this view, the observer's mind might not just perceive reality, but might actively participate in shaping it, especially at the quantum level. The role of the observer in quantum mechanics has long been a subject of fascination and debate. In traditional quantum theory, particles exist in a superposition of states, existing in multiple possibilities at once, until they are observed, at which point the wave function collapses into a single outcome. This phenomenon, known as the observer effect, raises profound questions about the role of consciousness in shaping reality. Is it our observation that causes the universe to choose a particular outcome, or is the universe already determined, and we are simply discovering what was always meant to be? The observer effect suggests that the act of measurement itself has a role in determining the state of a quantum system, implying that consciousness could play a direct role in influencing the very fabric of space-time. One of the most famous examples of this is the double-slit experiment, in which particles like electrons are fired at a barrier with two slits. When observed, the particles behave like particles, passing through one slit or the other. However, when not observed, the particles behave like waves, creating an interference pattern as though they pass through both slits simultaneously. This strange behavior has led many to suggest that the act of observation collapses the wave function, determining the outcome. Some interpretations of this experiment propose that consciousness itself is the key factor in determining which outcome is chosen. If consciousness can influence quantum events, this could have far-reaching implications for our understanding of reality. It raises the question of whether the universe is truly objective and independent of our perception, or whether it is in some way shaped by the minds that observe it. Could the universe itself be a kind of interface, presenting us with a version of reality that is shaped by the way we perceive it, rather than being an objective truth? This idea is explored in Donald Hoffman's interface theory of perception, which suggests that our perception of the world is not a direct representation of reality, but rather an interface, a system designed to help us survive by simplifying the complex underlying structure of the universe. According to Hoffman, our minds create a simplified model of reality, one that is useful for navigating the world, but not necessarily true to the deeper structure of the cosmos. Hoffman's theory suggests that what we perceive as reality may be a mere illusion, designed to help us interact with the world in ways that maximize our chances of survival. If this is the case, then consciousness is not just an observer of the universe, but an active participant in creating the version of reality we experience. This would imply that the universe is not simply a static entity, but a dynamic process shaped by the interaction between consciousness and the physical world. The role of consciousness in the cosmos is still a deeply mysterious and unresolved question. The idea that consciousness could influence the universe, shaping reality itself, challenges the very nature of space, time, and perception. Whether through Penrose and Hameroff's all-core theory, Bohm's holistic universe, or the observer effect in quantum mechanics, the connection between consciousness and the universe continues to push the boundaries of our understanding. As we explore these ideas, we begin to see that the universe might not just be a place to observe, but a dynamic system in which our awareness plays an integral role. Perhaps, in the end, the cosmos is not just a vast collection of stars and galaxies, but a living, breathing reality that is constantly being shaped by our minds. As we look to the future of cosmology, the question of what lies beyond the observable universe becomes more than just a philosophical curiosity. It becomes a challenge that scientists and researchers are actively working to address. The boundaries of the universe are not fixed. They are shaped by the tools we have at our disposal and by our ability to stretch the limits of observation. As our observational tools, computational power, and theoretical models continue to evolve, the prospects for discovering what lies beyond the observable universe grow more promising. So, how can we, with our current technologies and methodologies, hope to answer the age-old question of what lies beyond? One of the most exciting advances in cosmology is the development of next-generation telescopes, such as the James Webb Space Telescope, which is set to launch in the coming years. The James Webb Space Telescope is designed to be the most powerful space telescope ever built, offering unprecedented views of distant galaxies, stars, and other cosmic phenomena. Unlike the Hubble Space Telescope, which observes visible and ultraviolet light, the James Webb Space Telescope will focus on infrared light, allowing it to peer through cosmic dust and gas clouds to observe objects that are far beyond our current reach. This will give us a much clearer view of the early universe, allowing us to look back in time to when the first galaxies formed, and it could also reveal regions of space that are currently hidden from view. With this new data, scientists will be able to push the boundaries of our knowledge and potentially discover new regions of the universe that were previously unreachable. But telescopes alone may not be enough to fully understand the universe's edges. To truly unlock the mysteries of the cosmos, we must also explore the potential of quantum computing. Quantum computers, which use the principles of quantum mechanics to process information in fundamentally different ways from classical computers, could allow us to simulate vast regions of space. These simulations could help us model the behavior of distant cosmic phenomena, from the formation of galaxies to the dynamics of black holes. Quantum computing holds the promise of revolutionizing cosmology by enabling us to simulate and study the universe at a level of detail that was previously unimaginable. By running simulations that account for the complex interactions between matter, energy, and space-time, quantum computers could help us explore regions of the universe that are beyond our observational capabilities. This kind of computational power could also provide new insights into the very nature of the universe, including its structure, evolution, and the possibility of multiple dimensions. Beyond telescopes and computers, there are other ways in which we may be able to access the unseen regions of the universe. Gravitational waves, which are ripples in space-time caused by massive objects like colliding black holes or neutron stars, offer a new way to observe the universe. These waves travel across the cosmos, carrying with them information about distant events that would otherwise be invisible to traditional telescopes. The detection of gravitational waves has already opened up a new frontier in astrophysics, allowing scientists to study cosmic phenomena that were previously unreachable. As the technology for detecting and analyzing gravitational waves continues to improve, it may allow us to uncover hidden aspects of the universe, including regions beyond the observable horizon. Similarly, research into dark matter and dark energy, the mysterious substances that make up the majority of the universe's mass and energy, could provide valuable clues about the universe's structure and its limits. While dark matter and dark energy have not been directly observed, their effects can be seen in the way galaxies and galaxy clusters behave. Understanding these enigmatic forces could help us unlock new insights about the nature of space-time and the universe's expansion. If dark matter and dark energy are responsible for the unseen aspects of the universe, studying them might eventually reveal new regions of space and new ways to access parts of the cosmos that are currently beyond our reach. As we continue to make strides in these areas, the boundaries of the observable universe are likely to shift. The advancements in technology and the development of new theoretical models will allow us to study the universe in ways that were once thought impossible. Yet, even with all these advancements, there will always be questions that remain just beyond our grasp. The nature of space-time itself, the potential for hidden dimensions, and the true extent of the universe's infinite expanses may continue to challenge our understanding. One thing is certain: the more we learn, the more we realize that the universe is far larger, more complex, and more mysterious than we could have ever imagined. As our observational tools become more sophisticated and our theoretical models more refined, we will continue to push the boundaries of what we know. But even as we reach the farthest corners of the observable universe, we must remain open to the possibility that there are aspects of the cosmos that are simply beyond our understanding, at least for now. In the coming decades, the combination of advanced telescopes, quantum computing, gravitational wave detection, and dark matter research may unlock many of the secrets that lie beyond the observable universe. But as we continue to explore the cosmos, we are reminded that the more we discover, the more questions arise. Each new breakthrough opens the door to even greater mysteries, and the journey to understand the universe's edges and boundaries is one that will likely continue for generations to come. Ultimately, our quest to understand what lies beyond may not only deepen our knowledge of the universe, but also reveal the limits of our own perception and understanding, challenging us to expand our view of reality in ways we never thought possible. As we strive to understand the cosmos, we face an inevitable question. Are there limits to human observation and knowledge? Our senses, the tools we've developed, and even the way our minds process information shape the way we perceive the universe. It's not just about what we can see or measure. It's about the very structures of perception that define how we interact with reality. These limitations have profound implications for how we approach the cosmos and our quest for understanding. How much of the universe can we truly know? And will there always be aspects of reality that lie forever beyond our grasp? At the heart of this inquiry is the fact that our senses, those fundamental instruments through which we interact with the world, are limited. Human sight, for instance, is capable of perceiving only a small sliver of the electromagnetic spectrum. We can see visible light, but we cannot naturally perceive infrared, ultraviolet, or radio waves without the aid of technology. Our hearing is confined to a narrow range of sound frequencies, and our sense of touch can only detect a fraction of the forces and pressures in the world around us. Even with the most advanced instruments, like telescopes, particle accelerators, and gravitational wave detectors, we remain dependent on our ability to interpret data through human-centered technologies. Our tools, no matter how advanced, are still extensions of our limited sensory capacities, designed to bridge the gap between our innate perception and the vastness of the cosmos. This raises a profound question about the limits of human comprehension. How much of the universe can we understand if our senses only allow us to detect a fraction of what exists? The tools we've created, from telescopes to quantum computers, have allowed us to peer into distant galaxies, simulate quantum interactions, and uncover the mysteries of black holes. Yet every new discovery often leads to even more questions, and we are left to wonder whether we'll ever reach the full extent of what is out there. As we push the boundaries of technology, we also encounter philosophical challenges. Immanuel Kant, a philosopher from the 18th century, argued that the universe might forever remain beyond full comprehension due to the limitations of human experience. According to Kant, the structures of the mind itself shape the way we understand reality. He suggested that we cannot know the universe as it is in itself, only as it appears to us through the filter of our perception. This means that there may always be aspects of reality that remain hidden, not because we lack the right tools, but because the very way our minds are wired prevents us from fully grasping the totality of the cosmos. Kant's perspective offers a humbling view of the universe. It suggests that no matter how advanced our technologies become, there will always be limits to what we can know, and some aspects of reality may remain forever unknowable. Our understanding of the universe, Kant would argue, is shaped by the ways in which our minds interpret the data we gather, not necessarily by the true nature of the universe itself. This view doesn't mean that science is futile. Rather, it highlights the importance of recognizing the boundaries of human knowledge and the ways in which our minds influence the questions we ask about the universe. Even within the confines of our human limitations, science has made remarkable progress, continually expanding the boundaries of what is observable. However, the very nature of science requires an acceptance of uncertainty. Scientific knowledge is constantly evolving, and what we know today may be upended by a new discovery tomorrow. This is one of the key features of science. It is not a fixed body of knowledge, but a dynamic process, always open to revision and improvement. As Carl Sagan once said, "Science is a way of thinking much more than it is a body of knowledge. The scientific process is about asking questions, testing ideas, and adapting our understanding as we encounter new evidence. But as we continue to explore the universe, we're often confronted with phenomena that challenge our existing models, leading to the realization that the more we discover, the more there is to uncover. This is particularly true when we consider the vastness of the universe itself. The observable universe, limited to what we can see with telescopes, spans about 46 billion light-years, yet we know that this is just a fraction of the total universe. Beyond this observable limit lies an infinite expanse, one that we can never directly perceive or measure. This raises a central dilemma. How can we make meaningful scientific progress when we are unable to directly observe so much of what we seek to understand? The answer, in part, lies in our ability to make inferences and build models that extend beyond the boundaries of our direct observation. Through theoretical physics, we create models that help us understand the unseen, and through indirect evidence, like the detection of gravitational waves or the measurement of cosmic radiation, we can gain insights into regions of spacetime that are otherwise inaccessible. In the face of these limitations, imagination plays a crucial role in scientific discovery. Speculative theories, such as those about the multiverse, dark matter, and higher dimensions, allow us to push beyond the constraints of current observation, offering new frameworks for understanding the cosmos. Albert Einstein famously said, "Imagination is more important than knowledge." While this might seem counterintuitive, the importance of imagination in science cannot be overstated. It allows us to think beyond the known, to dream up hypotheses that challenge existing models, and to explore the unknown in ways that might one day lead to groundbreaking discoveries. Theoretical physics, in particular, relies heavily on imagination. Concepts like string theory, quantum mechanics, and the multiverse are based on speculative ideas that extend beyond direct observation. These ideas may not yet be provable with current technology, but they push us to think about the universe in fundamentally new ways. The role of imagination is not to provide concrete answers immediately, but to help guide the scientific process, offering new directions for research and providing the tools to address questions that may seem, at first glance, unanswerable. Equally important is interdisciplinary work, which allows us to approach problems from multiple perspectives. By combining ideas from physics, philosophy, mathematics, and even biology, we can gain a more comprehensive understanding of the universe. Just as the theories of Roger Penrose and Stuart Hameroff about consciousness and quantum mechanics require a fusion of physics and neuroscience, our quest to understand the cosmos requires collaboration across disciplines. Each field offers unique insights, and together they create a richer, more holistic view of reality. As we continue to push the boundaries of knowledge, we must remain mindful of the limitations that will always exist. Our senses, technologies, and cognitive structures will always shape the way we see the universe. But these limitations don't negate the importance of our pursuit of knowledge. Rather, they remind us of the vastness of what remains unknown and the need for humility in our search for understanding. Science, at its best, is about embracing the unknown and continually refining our models of reality. The journey to uncover the secrets of the universe may never be fully complete, but it is this very journey, driven by imagination, curiosity, and collaboration, that leads us to new insights and new horizons. As we reach further into the cosmos, we not only expand our knowledge, but also expand the very limits of what is possible to understand. For centuries, we have lived with the assumption that time and space are fundamental, basic building blocks of the universe, unchanging and constant. Time flows in a straight line, from past to present to future, while space stretches infinitely in all directions. It's so ingrained in our experience that we rarely question these concepts. But what if time and space, as we know them, are not actually fundamental aspects of reality? What if they are emergent properties of deeper underlying structures, only appearing to us as constants because of the way we experience the universe? This idea begins to shift the way we think about the fabric of the cosmos. Imagine for a moment that time and space are not permanent features of the universe, but rather patterns that emerge from something even more fundamental, something we might not yet fully understand. One of the most compelling theories to explore this idea is loop quantum gravity, developed by Carlo Rovelli and others. This theory challenges the traditional view of space-time as a smooth, continuous fabric. Instead, loop quantum gravity suggests that space-time itself is made up of tiny, discrete loops, like a mesh of interconnected nodes that form the very structure of the universe. In this theory, space and time are not continuous entities, but are instead made up of the smallest possible units, or quantum pieces. Just as matter is composed of atoms, space-time is thought to be composed of these fundamental indivisible chunks. This theory proposes that, at the most basic level, the universe operates on a quantum scale, where the smoothness of space-time as we experience it is an illusion, a larger-scale manifestation of these quantum properties. According to loop quantum gravity, space and time are not fundamental. They emerge from the quantum interactions that shape the universe at the smallest scales. This is a radically different way of thinking about the cosmos, one that could completely transform our understanding of reality itself. Even more radically, Julian Barber, a British theoretical physicist, has suggested that time itself may not exist at all, at least not in the way we think it does. In his book, The End of Time, Barber presents the idea of a timeless universe. According to Barber, time, as we experience it, is a human construct, a way for our minds to organize events in a linear sequence. But in reality, he argues, time does not flow or progress. Instead, all moments of time, past, present, and future, exist simultaneously as distinct, unchanging configurations of the universe. Barber's theory suggests that our experience of time is simply a feature of how we perceive change, not an actual fundamental part of the universe. In his view, the universe itself is not a timeline but a collection of moments, each of which is timeless in its own right. If Barber is correct, then our understanding of the universe would be completely upended. We would no longer think of the universe as moving forward through time, but rather as existing as a collection of timeless snapshots. What we perceive as the flow of time is simply our mental processing of changes in the configuration of the universe. The implications of this are profound. If time is not real in the way we experience it, then what happens when we step beyond our perception of time and space? How would our understanding of the cosmos shift if time itself were an illusion, a construct of the mind rather than a fundamental feature of the universe? The idea that time and space could be illusions challenges the very foundation of how we experience reality. It raises deep philosophical questions about the nature of existence. If time is not real, then how do we make sense of the events in our lives? How do we understand the aging process, or the movement of the stars across the sky? Our whole conception of the world around us is rooted in the idea that time flows and space exists as we perceive it. But if these are not fundamental but rather emergent properties, then the universe might operate in ways far more complex than we can currently imagine. The question of time as an illusion also ties into broader debates about the nature of reality itself. Could it be that our perception of the universe is not an accurate reflection of what truly exists? This idea aligns with David Bohm's work on the holistic universe. Bohm proposed that the universe is not a collection of independent parts, but rather an interconnected whole, where every part is deeply linked to every other. According to Bohm, the apparent separateness of objects in space and time is just a superficial illusion, a projection of a deeper, more unified reality. In his view, space and time, as we experience them, are merely constructs of the mind, created to help us navigate the world, but not reflective of the underlying structure of the universe. Bohm's implique order suggests that reality is fundamentally interconnected in ways that transcend our linear experience of time and space. The true nature of the cosmos, according to Bohm, is not something that can be fully understood through our conventional perception of the world, but is a deeper, non-local reality that cannot be fully captured by the senses. If we begin to entertain the idea that time and space are illusions, it opens up intriguing possibilities for what lies beyond the observable universe. What if the universe, in its truest form, exists outside the boundaries of time and space altogether? Could the mysteries of dark matter, dark energy, or the true nature of gravity be tied to these hidden, non-local dimensions of reality? And if time itself is not a constant, how might we explore the universe in ways that go beyond our temporal limitations? Could the key to understanding the cosmos lie in stepping beyond the framework of time and space as we know them and learning to perceive reality in entirely new ways? These questions bring us to the very limits of human understanding. If time and space are not fundamental, then what is the true nature of the universe, and how can we even begin to comprehend it? The answer may lie in expanding our conceptual horizons, using imagination and interdisciplinary approaches to bridge the gap between perception and reality. As physicists, philosophers, and cosmologists continue to explore these radical ideas, we may discover that the boundaries of the universe are not just physical, they're cognitive, shaped by the limits of human experience. The more we delve into the idea that time and space are illusions, the more we come to realize that the universe may be far more strange and complex than we could have ever imagined. As we explore the depth of quantum mechanics, cosmology, and consciousness, we begin to see that the fabric of reality is not as simple as it once seemed. The universe, it turns out, may not be a static, unchanging place, but a dynamic, ever-evolving process that we are only beginning to understand. Time, space, and reality itself may be far more fluid, interconnected, and mysterious than we can currently fathom. And as we continue to explore these ideas, we may uncover a deeper, more profound truth about the universe and our place within it. The notion of infinity has fascinated humans for millennia, and when we apply it to the universe, the implications become mind-boggling. As we peer deeper into the cosmos, one of the most compelling questions emerges. Is the universe truly infinite, stretching endlessly in all directions? Or is there some hidden boundary, some ultimate edge beyond which the universe cannot go? These questions challenge the very fabric of cosmology and force us to confront the limitations of human understanding, especially when we consider that we can only observe a small fraction of what may exist. What if the universe extends far beyond our observable horizon, into realms that we can't even begin to comprehend? And if infinity is at play, what does that mean for the future of cosmological research and human perception? One of the most striking ideas to emerge from modern cosmology is the potential for an infinite universe, one that has no end, no boundary, and no limit. This idea suggests that the universe could stretch on forever, beyond the furthest galaxies and stars we can see, with no true edge. The observable universe, which extends about 46 billion light-years from Earth, is only the region from which light has had time to reach us since the Big Bang. However, beyond this observable horizon, it's possible that space continues infinitely, expanding at a rate faster than the speed of light. This is not just a faraway concept. It's deeply tied to the way the universe is structured at its most fundamental level. Cosmologists and physicists have long speculated that our observable universe might just be one small part of a much larger whole, and the multiverse theory provides one of the most intriguing frameworks for exploring this idea. The multiverse suggests that what we perceive as our universe could be just one of many, each with its own set of physical laws and constants. In this view, our universe is like a single bubble floating in an infinitely expanding sea of other universes, each unique in its own way. Some of these universes may be vastly different from our own, with entirely different laws of physics, while others may be similar but slightly altered. The idea of infinite universes raises profound philosophical questions about our place in the cosmos. If the universe is infinite, then the very concept of limit begins to lose meaning. The observable universe, which we so often think of as the edge of existence, may simply be a temporary illusion. Our current horizon based on the tools and instruments we have. The reality that lies beyond that horizon might be just as vast, if not more so, than what we have already observed. And if the multiverse is true, then the cosmos could contain an infinite number of parallel realities, some of which could be entirely inaccessible to us. Each of these universes could stretch out endlessly, contributing to an eternal, ever-expanding web of existence that goes far beyond the reaches of human perception. The idea of infinite space brings with it a number of paradoxes. One of the most striking is how we reconcile the concept of infinity with the limitations of human experience. After all, our senses are finely tuned to perceive only a small slice of the universe. Our ability to understand the cosmos is constrained not only by the limitations of our tools, our telescopes, particle detectors, and even our theoretical models, but also by the very nature of human perception. We are creatures built to experience the world in finite terms, and our minds have evolved to deal with finite observable realities. Infinity, in this sense, is almost beyond our comprehension. How can we even begin to grasp the idea of something that has no end, that stretches forever in every direction? This paradox lies at the heart of our exploration of the cosmos. We use abstract concepts, like mathematical models and theoretical physics, to extend our understanding beyond the limits of direct observation. Yet no matter how advanced our instruments become, there will always be a part of the universe that remains unreachable, inaccessible to human perception. The limits of observation mean that no matter how many billions of light years we can see with our most powerful telescopes, the true extent of the universe remains a mystery. We may never know exactly how far it goes, or whether it continues indefinitely, but the pursuit of these answers drives the ongoing quest to push the boundaries of science. One of the most important aspects of this inquiry is how human imagination and curiosity have been central to advancing our understanding of the cosmos. The theories and models that have shaped our view of the universe, like the Big Bang theory, the idea of cosmic inflation, or the multiverse hypothesis, are all the products of human creativity and speculative thinking. These ideas allow us to imagine what we cannot directly see and offer new ways to think about the universe and our place within it. Through imagination, we can develop models of the cosmos that stretch our understanding beyond the limits of our senses, imagining realms of existence that lie beyond the observable universe. Speculative theories, such as those about higher dimensions, black holes, and the multiverse, expand the boundaries of scientific inquiry. They suggest that the universe might be far more complex and multifaceted than we have considered, with regions that exist beyond our reach and laws of physics that we have yet to fully understand. These ideas might not always be directly testable with current technology, but they push the limits of what we can imagine, offering new perspectives on the nature of reality. In a way, they provide a roadmap for future discoveries, inviting us to look beyond the known and imagine what lies beyond the horizons of our perception. As we continue to explore the cosmos, our understanding of infinity and the limits of the observable universe will evolve. Each new discovery, whether it's the detection of gravitational waves, the observation of distant exoplanets, or new insights into the nature of dark energy, brings us one step closer to uncovering the true structure of the universe. But even as we expand our knowledge, we are reminded that there may always be aspects of the cosmos that lie beyond our grasp, regions that remain hidden due to the limitations of time, space, and human perception. This doesn't mean that the search for answers is futile, rather it underscores the vastness of the unknown and the endless potential for discovery. At the same time, the concept of infinity invites us to reflect on the nature of existence itself. If the universe is infinite, then the possibilities for what could exist beyond the observable universe are limitless. There may be regions of space and time that stretch out into unimaginable expanses, full of phenomena that challenge our understanding of the laws of physics. The very idea that the universe could be infinite also raises questions about our place in it. How significant are we as observers in the grand scheme of an endless cosmos? And how do we reconcile our finite experience of the world with the infinite possibilities that might exist? Ultimately, the exploration of the infinite challenges our perceptions of reality and forces us to expand our thinking about what the universe might be. We may never fully understand the true extent of the cosmos, but in our quest to know what lies beyond, we continue to push the boundaries of science and imagination. And in doing so, we discover that the journey itself, the search for the unknown, is as important as the answers we seek. The infinite universe, with all its mysteries, is a reminder that we're always on the edge of discovery, always reaching for something just beyond the horizon. As we look to the future of space exploration, we're on the cusp of a new era that promises to reveal the deepest secrets of the cosmos, potentially uncovering knowledge far beyond the limits of what we can currently observe. The next few decades could usher in a revolution in how we study space, with advancements in technology and new theoretical models pushing the boundaries of what we thought was possible. This exploration is not just about venturing farther into space, but about looking at the universe in new, innovative ways that could radically transform our understanding of the cosmos. One area that's already showing great promise is gravitational wave astronomy. Gravitational waves are ripples in the fabric of space-time caused by the movement of massive objects, such as black holes merging or neutron stars colliding. These waves, first detected in 2015, carry information about the most extreme events in the universe, providing a new way to listen to the cosmos. While traditional telescopes allow us to observe light, gravitational wave detectors open up a whole new sense for exploring space. As our ability to detect these waves improves, we could uncover hidden aspects of the universe, like the inner workings of black holes, or the events occurring in the farthest reaches of space that were previously beyond our observational capabilities. Alongside gravitational waves, the study of quantum mechanics will play an increasingly important role in future space exploration. Quantum mechanics governs the behavior of particles at the smallest scales, but its mysteries still confound even the most advanced scientists. The integration of quantum physics with cosmology could eventually lead to breakthroughs in understanding the fundamental nature of the universe, including its origins, structure, and the hidden connections between the forces of nature. As quantum technologies, like quantum computers, advance, they may allow us to simulate and explore parts of the universe that were once thought to be out of reach, providing insights into the behaviors of the universe on both the largest and smallest scales. The search for dark matter and dark energy, the mysterious substances that make up about 95% of the universe, will also play a critical role in expanding our understanding of the cosmos. Although we cannot yet directly observe these phenomena, their effects can be seen in the way galaxies move and in the accelerated expansion of the universe. Dark matter, for example, seems to exert a gravitational pull that affects the motion of galaxies, yet it doesn't interact with light, making it invisible to traditional telescopes. Dark energy, on the other hand, appears to be driving the accelerated expansion of the universe. As new experiments and technologies are developed, we may finally uncover the true nature of dark matter and dark energy, revealing the invisible forces that shape the universe's expansion and structure. One of the most exciting projects on the horizon is the Square Kilometre Array, SKA, an enormous radio telescope network that is set to become one of the most powerful instruments ever built for exploring the universe. The SKA will be spread across 2 continents, with over 1,000 antennas working together to capture signals from the farthest reaches of space. The SKA will allow scientists to map the cosmos in unprecedented detail, providing a clearer picture of how galaxies form, how stars and planets evolve, and how the universe behaves on large scales. But perhaps most excitingly, the SKA will help us peer deeper into space than ever before, potentially revealing hidden regions of the universe that were previously undetectable. This could include regions of space that lie beyond the observable universe, as well as phenomena that challenge our current models of physics. As we develop more advanced tools and techniques, we may also be able to detect dark energy directly. Currently, we only observe its effects, its influence on the acceleration of the universe's expansion, but understanding its true nature is one of the greatest challenges in cosmology. One possibility is that future missions or instruments may be able to measure the effects of dark energy in more precise ways, perhaps revealing new dimensions of space-time or even helping us understand the shape of the universe itself. Detecting dark energy could open the door to entirely new fields of research and change the way we think about the universe's past, present, and future. Another exciting avenue for future discovery is the detection of cosmic relics, remnants of the Big Bang that could provide key insights into the early universe. Cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang, has already given us a glimpse into the universe's infancy, but there may be other relics hidden in the cosmos. Some scientists are exploring the possibility that traces of primordial particles, magnetic fields, or other unknown entities could still be detectable today, offering a snapshot of the universe as it existed billions of years ago. These relics could serve as cosmic time capsules, preserving the history of the universe long before stars, galaxies, or even atoms formed. Looking ahead, the future of space exploration holds immense promise. As our technological capabilities continue to advance, we will gain new ways of observing the universe that may revolutionize our understanding of its origins, structure, and future. Instruments like the James Webb Space Telescope will allow us to look further into space, and further back in time, than ever before, shedding light on the first galaxies, stars, and planets to form after the Big Bang. New missions to explore distant exoplanets and moons within our solar system may also reveal environments that could support life, expanding our view of what is possible in the cosmos. However, despite these exciting advances, we must also acknowledge the vastness of what remains unknown. As we continue to push the boundaries of what we can observe, we are constantly confronted with the reality that there will always be aspects of the universe that lie beyond our reach, whether because they exist beyond the observable universe, or because they are simply too far or too faint for us to detect. This doesn't mean the pursuit of knowledge is futile. Rather, it highlights the vastness of the universe and the endless possibilities that lie ahead. In many ways, the future of space exploration will be shaped not just by new technologies, but by the spirit of human curiosity and imagination. Every time we look deeper into the cosmos, we open new doors to discovery. Our imagination, our willingness to dream beyond the boundaries of what we know, will continue to drive the quest to understand the universe and everything that lies beyond. What we discover in the coming years may forever change our understanding of the cosmos, just as past discoveries, like the discovery of galaxies beyond our own or the detection of gravitational waves, have done. The future is full of endless possibilities, and the journey of exploration is just beginning. When we think about the universe, we often imagine it as having clear boundaries, defined edges where space ends, and beyond which there is nothing. We speak of the observable universe, as if it marks the limit of the cosmos itself, and consider the idea of boundaries as a fundamental part of our understanding of the universe. But what if these boundaries, these edges, are not truly physical, but are simply constructs of our perception and understanding? What if the limits we see are not intrinsic to the universe, but the result of the tools and frameworks we use to observe it? To explore this idea, we need to reconsider the concept of boundaries in cosmology. The boundaries we discuss, such as the edge of the observable universe or the cosmic horizon, are based on what we can observe and measure, limits set by the speed of light, the expansion of space, and the age of the universe. These boundaries mark the limits of our observational capabilities, but they are not necessarily fixed features of the universe itself. In fact, some of the most intriguing ideas in modern physics suggest that the boundaries we perceive may be temporary or even illusory. One of the most influential physicists to challenge the traditional notion of boundaries is John Archibald Wheeler. Wheeler, known for his work on general relativity and quantum mechanics, proposed a radical view of the universe as an information-based system. In his participatory anthropic principle, Wheeler suggested that the universe exists not as a static entity, but as an ongoing process, deeply intertwined with the act of observation. According to Wheeler, the universe is not something separate from us that we simply observe, but something that is actively shaped by our interactions with it. In this framework, boundaries in the universe, such as the edge of the observable universe, are not absolute but subjective constructs influenced by the way we measure and perceive them. For Wheeler, the idea of boundaries is tied to the very nature of information. In his view, the universe is fundamentally composed of information, and our understanding of the cosmos is based on how we gather and process that information. The boundaries we perceive are not fixed, but are constantly shifting as we gain new insights, develop new technologies, and refine our understanding of the universe. In this sense, what we think of as a boundary is not an actual, unchanging edge to the universe, but a temporary marker of our current observational limitations. The boundary is not a static feature of the universe. It is an ongoing process of discovery and understanding. This perspective challenges the conventional view of the universe as a static, finite system with defined edges. Instead, it suggests that the universe is a dynamic, ever-evolving entity, constantly expanding and changing. The limits we perceive are not permanent fixtures but markers of the current state of our knowledge. As we develop new tools and technologies, such as next-generation telescopes or gravitational wave detectors, We will continue to push the boundaries of what we can observe, revealing new regions of space and new phenomena that were previously hidden from view. In this sense, the boundary of the observable universe is not the end of the cosmos, but a temporary horizon, waiting to be expanded as our observational capabilities grow. Another fascinating idea comes from theories suggesting that the observable universe is part of a greater, ongoing cosmic interaction. In this view, the universe is not a static, isolated entity, but a dynamic system in constant flux, shaped by interactions that go beyond our immediate perception. These interactions might occur on scales that are currently beyond our reach, but they could influence the behavior of the universe in ways we're only beginning to understand. For example, the universe could be part of a vast interconnected web of cosmic processes, where events in one part of the universe can ripple across space-time and affect distant regions. In this framework, what we perceive as a boundary might simply be a marker of where our current observational tools can reach, rather than an actual limit to the universe itself. This idea ties into the notion that space and time, as we perceive them, are not fundamental aspects of the universe, but are emergent properties arising from deeper underlying structures. Some physicists propose that space and time may not exist at all in the traditional sense, and that what we experience as the fabric of space-time is simply a manifestation of more fundamental quantum processes. In this view, the boundary of the observable universe is not a physical edge, but a limit imposed by our current understanding of space-time. As our understanding evolves, these boundaries could shift, revealing new dimensions of the cosmos and transforming the way we think about the universe. The concept of boundaries also raises important philosophical questions. If the boundaries we perceive are merely constructs of our perception, then how do we define the true nature of the universe? What does it mean to know the universe if the limits of knowledge are constantly changing? The idea that boundaries are not absolute challenges our understanding of what it means to be human. How do we reconcile our finite experience of the world with the infinite cosmos? How can we comprehend something that may have no true edge, no final frontier? One possible way to approach this challenge is by embracing the idea that our perception of the universe is always limited, but that this limitation does not define the universe itself. Instead, we can view the boundaries as markers of where our current understanding stops, rather than as fixed, immutable features of the cosmos. As we continue to explore, as our observational tools improve and our theories evolve, the boundaries of the universe will shift, revealing new layers of reality and uncovering deeper cosmic mysteries. In many ways, the question of boundaries in cosmology is tied to our own curiosity. Our desire to understand the universe is what drives us to look beyond the limits of our perception and to imagine new possibilities for what might exist beyond. The boundaries we perceive today may be the starting point for future discoveries, and as we continue to push the edges of our knowledge, we will uncover new realms of existence, new phenomena, and new ways to explore the universe. Ultimately, the concept of boundaries is not something that limits us, but something that inspires us to reach further, to question more deeply, and to seek the unknown. As we look to the future of cosmology, the question of boundaries will remain central to our understanding of the universe. Will we ever reach the true edges of the cosmos, or will we find that the universe has no boundaries at all? The answer may lie not in the physical limits of space, but in our ability to expand our minds, our tools, and our theories to reveal new dimensions of reality. What we call boundaries today may simply be markers of where we are now, and as we continue to explore, those boundaries will continue to shift, leading us into ever deeper understanding of the universe and the profound mysteries that lie beyond. As we stand on the brink of new discoveries in cosmology, the ultimate question remains: can we find a unified theory that explains not only the universe we observe, but also what lies beyond our observational limits? The idea of a unified theory, one that brings together the seemingly disparate forces of nature, has been a goal for physicists for over a century. With the vast complexities of the cosmos unfolding before us, a single framework capable of explaining the origins of the universe, its current state, and its future would be a monumental achievement. But what would such a theory look like, and how might it reveal answers to some of the most profound questions about space, time, and the limits of the known universe? A unified theory of cosmology would need to reconcile the two pillars of modern physics: quantum mechanics and general relativity. These two frameworks have been incredibly successful in their respective domains. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the workings of gravity and the large-scale structure of the universe. However, the two theories are fundamentally incompatible in their current forms. While general relativity describes a smooth, continuous space-time, quantum mechanics operates in a world of probabilities and uncertainty. To create a unified theory, we would need to find a way to bring these two perspectives together, allowing us to describe both the very small and the very large within a single, cohesive model. One of the most promising candidates for such a unified theory is string theory. String theory suggests that the fundamental building blocks of the universe are not point-like particles, as we've traditionally thought, but tiny, vibrating strings. These strings vibrate in multiple dimensions, and the different modes of vibration correspond to different particles. String theory posits that the universe exists in more than the familiar 3 dimensions of space and 1 of time. Instead, there could be additional dimensions, tiny curled-up spatial dimensions that we cannot directly observe. By incorporating these extra dimensions, string theory provides a framework that could, in theory, unify quantum mechanics and general relativity. In this view, the universe is not just a collection of particles interacting in space-time, but a vast interconnected system where everything, from the smallest particles to the largest galaxies, is part of a single, vibrating fabric. Several physicists have made important contributions toward developing a unified theory, and one of the most notable names is Brian Greene. Greene has been a leading advocate for string theory and has worked extensively to develop its implications for our understanding of the universe. In his book, The Elegant Universe, Greene explains how string theory could provide a theory of everything, offering a single framework that unites the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force and the weak nuclear force. String theory's ability to describe these forces in a unified way has led many to hope that it will provide the missing piece of the puzzle in understanding the cosmos. Another important figure in this search for unity is Michio Kaku, whose work on M-theory extends the ideas of string theory even further. M-theory proposes that the fundamental objects of the universe are not just one-dimensional strings, but higher-dimensional objects known as branes. These branes could have multiple dimensions, and the entire universe may exist on one of these branes, floating in a higher-dimensional space. According to M-theory, the universe we observe may be just one slice of a much larger, multi-dimensional reality, where different universes exist on separate branes. This idea expands the concept of the multiverse, suggesting that there could be entire parallel universes, each with its own physical laws and constants, all interacting within a higher dimensional space. By extending string theory into M-theory, Kaku and others hope to create a more complete framework that explains the nature of the universe and the interactions between its different dimensions. As we look toward the future of cosmological research, the breakthroughs in physics that could reveal answers to what lies beyond the observable universe are on the horizon. With advancements in technology, we are getting better at observing the distant cosmos. Next-generation telescopes, such as the James Webb Space Telescope, will allow us to peer further into space and time, potentially providing new insights into the universe's earliest moments and uncovering hidden regions of space that were previously out of reach. But even with these advancements, the true nature of the boundaries beyond the observable universe remains uncertain. Could the universe stretch on infinitely? Or is there a limit to how far space extends? The study of dark energy and dark matter could also offer critical insights into the structure of the cosmos beyond what we can currently observe. These mysterious substances make up the majority of the universe's mass and energy, yet we have yet to directly detect them. Dark energy, which is believed to be responsible for the accelerated expansion of the universe, may hold the key to understanding the universe's true nature and its ultimate fate. Similarly, dark matter, which exerts gravitational influence on galaxies but does not interact with light, could reveal hidden aspects of the cosmos that we can only infer through its effects. Understanding these forces could help us uncover new regions of the universe and provide a clearer picture of its overall structure. One of the central questions a unified theory could address is the very nature of the cosmic horizon, the boundary beyond which we cannot observe. While this boundary is defined by the limitations of the speed of light and the expansion of space, a unified theory could help us understand whether the observable universe is the true extent of the cosmos or just a small piece of a much larger, infinite structure. If the universe is indeed infinite, as some theories suggest, then the concept of boundaries might not apply in the traditional sense. The cosmic horizon may be simply the limit of our perception, and as our observational tools improve, that horizon may continue to shift outward, revealing more of the universe's true vastness. The quest for a unified theory also brings with it philosophical implications. If we are able to uncover a single framework that explains all the forces of nature and the structure of the universe, it would mark a profound shift in our understanding of reality. It would not only change the way we perceive the cosmos, but also redefine our place within it. The idea of a unified theory is, at its core, about finding coherence in a universe that often feels chaotic and unpredictable. It is about connecting the dots between the smallest quantum particles and the largest cosmic structures, seeing them as part of a larger interconnected whole. Ultimately, the search for a unified theory is a journey, one that may take us to the farthest reaches of the universe and beyond. As we continue to push the boundaries of space exploration and refine our theories, we will undoubtedly uncover new insights that challenge our current models and open new doors to discovery. Whether it's through string theory, M theory, or new advancements in quantum mechanics, the future of cosmology holds the promise of deeper understanding and greater clarity. The answers to what lies beyond the observable universe may not be immediate, but the search itself will continue to expand the limits of human knowledge and imagination. Throughout this exploration, we've ventured into some of the most profound questions of cosmology. What lies beyond the observable universe? What does it mean to reach the boundaries of the known cosmos? And how do speculative theories help us peer into the unknown? We began by examining the concept of the observable universe, the vast expanse that we can detect with our instruments, extending some 46 billion light-years from Earth. This boundary is not an edge of space, but rather a limit of what light has had time to reach us since the universe began. Beyond this, regions of space remain hidden from view, fueling curiosity about the mysteries that lie beyond. From there, we ventured into speculative theories, where we learned that the universe may not have a definitive edge at all. The multiverse theory suggests that what we observe as our universe could be just one among countless others, each existing within a larger infinite fabric of reality. Quantum mechanics, relativity, and even string theory have proposed that our understanding of space and time may be far from complete. There could be hidden dimensions, unknown forces, or entire realms of existence yet to be discovered. The very idea that time, space, and even reality itself may be illusions, shaped by our perception, has opened up new avenues for exploring the cosmos in radically different ways. We discussed some of the most innovative ideas in modern cosmology, from loop quantum gravity, which challenges traditional notions of space-time, to M theory, which proposes that our universe may be just one brain floating in a higher dimensional space. Theories like these raise as many questions as they answer, yet they push us closer to a deeper understanding of the universe's true nature. We've also reflected on the role of consciousness and perception in shaping the reality we observe. Could our awareness influence the cosmos, shaping the very fabric of space and time in ways we cannot yet understand? Even with these remarkable theories, one thing remains clear. The universe is far more mysterious and expansive than we can currently fathom. And while we may never fully answer all the questions about what lies beyond the observable universe, the pursuit of knowledge will continue to reveal new layers of mystery, understanding, and wonder. Each discovery we make, from the detection of gravitational waves to the next-generation space telescopes like the James Webb Space Telescope, brings us one step closer to uncovering the secrets of the cosmos. In the end, it's not just about the answers we find, but the questions we ask along the way. The journey of discovery itself is just as important as the destination. For every new breakthrough sparks a wave of curiosity, fueling our desire to look deeper, to explore further, and to understand more about our place in the infinite universe. As we reflect on the vastness of the cosmos, let us remember that we are all part of this unfolding story, a story that stretches far beyond what we can see and touches the very essence of existence. The pursuit of knowledge will continue to shape our understanding, and with each step forward, we uncover new mysteries and reveal the endless possibilities that await. The universe, in all its complexity, invites us to continue exploring, knowing that the journey is just as important as the discoveries we make along the way.